Hello students, Deepak Pandey here in the 7th episode of Breaking Gate 2020 in 45 days, and this episode will be based on the discussion on energy balance. So what is energy balance? Just like mass balance, you have conservation of energy as well. So energy cannot be created or destroyed. It can only be transformed from one form to another form, right? Or it can only be transferred from one system to another system or between the system and the surroundings. So the energy balance is energy in minus out is equal to accumulation. Fine. So when you involve all types of energies entering the system, leaving the system, now energy can enter the system in the form of mass, in the form of heat, in the form of work, and it may leave from the system in the same form. So when you do all these, when you involve everything in your equation, then at steady state, your energy balance equation becomes. So I'm giving you the final form. Let us not go into the detailed derivation. We will just learn how to use that final form. At steady state, the equation becomes delta H is equal to Q external. Now this equation in this form can be used in various subjects, not only in process calculation, but in process calculation, in mass transfer, in reaction engineering, in all the cases, right? Now let me explain these terms separately. What is delta H? What is Q externals? Once you know the meaning of these two terms, then you can always solve the problem easily. Q external is the amount of heat added to the system from outside or removed from the system to the surroundings. That is why I am using the word external. So it is Q external is the heat added to or removed from the system. Heat added to or removed from the system. So suppose if the question says that you are adding 100 kilojoule of energy to the system, or the question says if you are removing 50 kilojoule of energy from the system, right? So we have learned the sign convention which is there in thermodynamics as well as in heat transfer, that when heat is added to a system, it should be considered as positive, and when heat is removed from the system, it should be considered as negative. So this equation has been developed by using the same sign convention. Suppose you are adding 100 joule to the system, then Q external you should write as 100. If you are removing 50 joule from the system, then you should write Q external as minus 50. Okay. But suppose if the question asks that what is the amount of heat removed from the system, then you should not write Q external as minus Q external. You see, keep simply it as Q external. Automatically it is going to give you the answer Q is equal to minus 50, right? So when the values are given in the problem, put the values along with sign. But if Q external is only asked, then just keep it as it is. Automatically it is going to give you positive or negative value, and then you will come to know whether heat is being added to the system or removed from the system. Right. Now in this equation, what is delta H? Delta H is change in enthalpy, as the symbol suggests. And what is change in enthalpy? Suppose if the system is non-reacting, let's call it as change in enthalpy, right? Suppose if the system is non-reacting, so there is no reaction, fine. And in that case, for non-reacting systems, delta H is equal to summation of Fi Hi cap for all the output streams minus summation Fi Hi cap for all the input streams. Fine. You can also write the enthalpy as Fi into Cpi into Ti minus T reference for in output minus Fi into Cpi into Ti minus T reference for input. Fine, because enthalpy is calculated as the flow rate multiplied by the Cp multiplied by the temperature minus T reference. So that can also be substituted here. Means you can write this as summation for all the output streams, and you can have here Fi Cpi, right, Ti minus T reference for the output stream minus summation Fi Cpi Ti minus T reference for the output stream, that is delta H. Please note that delta H is out minus in, not in minus out. No need to get confused here. You have studied that energy in minus energy out is equal to accumulation. That is also correct. This formula is derived from the same equation, and if you are using this, then always put delta H as this. Now what is F here? F is the molar flow rate, Cp is the specific heat of the component I present in the output, Ti is the temperature. Now all the components will be at the same temperature, of course, in the output stream, and Ti here is the temperature of the input stream. So F denotes the molar flow rate and Cp denotes the specific heat. Fine. So that is the case if the reaction, if the system is non-reacting, right? Suppose if reaction is also taking place, then how you write? For reacting systems. Now you can use this equation in chemical reaction engineering as well. For reacting systems, now this is your delta H, and this delta H must be equal to the Q external. Fine. If system is reacting, in that case, you can write delta H is equal to summation Fi Cpi for the output streams multiplied by temperature of the output stream minus the reference temperature minus summation Fi Cpi temperature of the input stream minus the reference temperature for all the input streams, right? Plus enthalpy of a reaction, right? This enthalpy of reaction should be calculated at the reference temperature only. Now here is an important point. Suppose in a question, if standard enthalpy of reaction is given, right? Now standard enthalpy of reaction is always calculated at 25 degrees Celsius or 298 Kelvin. So it means that you have to select 298 Kelvin as the reference temperature. Suppose if the enthalpy of reaction is given at 500 Kelvin, you should select 500 Kelvin as your reference temperature. In this case, you can select any temperature as your reference temperature, doesn't matter, it is going to be cancelled. So this is the enthalpy of reaction at the reference temperature multiplied by Fa0 into Xa, where Fa0 is the molar flow rate of A, which is the limiting reactant, multiplied by the conversion of the reactant should be equal to the Q external, right? Now here there is an important point, that we have to use the enthalpy of reaction along with sign. What does it mean? Suppose that you are having exothermic reaction. So exothermic reaction, enthalpy of reaction is always negative, fine. So along with the sign means the enthalpy of reaction is, it is suppose minus 50, so it should be put as minus 50 here, right? Fa0 is the initial moles of the limiting reactant, Xa is the conversion of the limiting reactant. Fine. So this is the left hand side and this must be equal to Q external. Okay. Suppose if the system is adiabatic. So definitely if the system is adiabatic, there is no heat exchange with the surroundings and therefore Q external should be 0. So if the system is adiabatic and non-reacting, in this equation put Q external is equal to 0. If the system is reacting and again adiabatic, in this equation put Q external is equal to 0. Suppose there was a question in GATE where there was no reaction but it was a mixing process. So how to handle that? How to write energy balance equation for mixing? Again, there is no change in these equations. You can always use delta H is equal to Q external, but there you can write delta H as summation of Fi Cpi Ti minus T reference for output minus summation Fi Cpi Ti minus T reference for input. Now there is no reaction, so I cannot write enthalpy of reaction into Fa0 into Xa, but definitely there is some enthalpy of mixing, right? So you should write whatever enthalpy it is, you just add in this equation. If it is enthalpy of neutralization, add it. If it is enthalpy of decomposition, add it. Fine. Now this thing must be multiplied by some quantity. I'll explain why, and this is equal to Q external. Fine. If you see, this is the energy balance, and if you check the unit of each and every term here, what is the unit? The unit is always energy by time, kilojoule by second, joule per hour, joule per second. Fine. Now the enthalpy unit is always energy by mass. Fine. So in this case also, enthalpy of reaction is like kilojoule per kg or kilojoule per mole. So you have to multiply this by mole per second so that you can get kilojoule per second, right? Similarly here, enthalpy of mixing is generally given as kilojoule per kg. So unless you multiply it by kg per second, I am not multiplying this enthalpy of mixing by a term because I do not have the question right now and do not have the proper information here. So whatever proper information is given to you in the problem, just multiply so that you can get the unit of energy by time. If you are getting the unit energy by time, units are getting cancelled, then the equation is perfectly fine, and that must be equal to Q external. So if you use these equations in your energy balance, whether it is in process calculation or it is in CRE, most of the students have doubt that the energy balance of process calculation is different, energy balance of CRE is different. No, they are totally same, and in fact energy balance is everywhere same, fine. But in some subjects we can simplify the energy balance to a greater extent, while in other subjects we have to use more complex form of energy balance equation. This one is quite simplified. How it is simplified? Delta H is equal to Q external. It assumes a number of things. First thing, that it is only applicable to steady state. Second thing, that there is no delta KE and delta PE. Means while deriving this equation, during the derivation at some step we are neglecting the change in kinetic energy and the change in potential energy. Also we assume that there is no shaft work. So when all these assumptions are there, you have the equation enthalpy change is equal to Q external, right? Now before solving any problem on energy balance, you should check one thing, and what is that? That is the unit of Cp, specific heat. What is the unit of Cp? If you see the units, it is sometimes kilojoules per kg per Kelvin, and some other times in some other problems it is kilojoule per mole per Kelvin, right? So suppose if the unit of specific heat is kilojoule per kg per Kelvin, then specific heat cannot be multiplied by molar flow rate. It is obvious. If it is the unit is kilojoule per kg per Kelvin, then it should only be multiplied by the mass flow rate, right? And if it is kilojoule per mole or per kilomole per Kelvin, that it should only be multiplied by the molar flow rate. In these equations, I am multiplying all the specific heat values by the molar flow rate. It means that I am assuming that the units of specific heat are kilojoule per mole per Kelvin. So I hope the equation is clear to you how to write energy balance. Fine. Now I'm going to take some examples. Let's take 2 examples so that the concept, the application of this equation becomes more clear. Okay. This problem is from year 2004, and that is based on energy balance and some concepts of mass balance with chemical reaction as well. So let us spend a minute for reading the problem. 1 mole of methane means basis is given, right? So while you read the problem, also plan the strategy accordingly during reading the problem, right? So 1 mole of methane undergoes complete combustion, right, in a stoichiometric amount of air. What is the meaning of stoichiometric amount of air? Now that is an important concept. Stoichiometric air means whatever amount is required for reacting completely with methane, only that much amount of air is passed. No excess amount of air is passed. That is the meaning of stoichiometric amount, okay? The reaction proceeds as it is given. The enthalpy of reaction is given. The enthalpy is negative. It means that the reaction is exothermic, and the enthalpy is calculated at a temperature of 298, right? So it is 298 Kelvin, of course, which is 25 degrees Celsius. It means that what should be the reference temperature for solving this problem? Either 25 degrees Celsius or 298 Kelvin. Now the first question is, mole fraction of water vapor in the product gas is about. Now this question is based only on mass balance. I hope you can solve this one. And the second case, if average specific heat, why they are using the word average? Because specific heat is a function of temperature, as well as it depends if the mole fraction is also changing. So if they are saying average, it means you need to worry about nothing. Just one specific heat is given, and whatever component is there, you have to take specific heat as same. and that is 40 joule. Another point you have to take care of is this. It is the units of specific heat is joule per mole. It means that you have to write the energy balance in terms of moles. The maximum temperature rise of the exhaust gases in degrees Celsius is approximately. Now they are asking the temperature rise, right? Now what is the meaning of temperature rise? The input temperature is not given, inlet temperature is not given, means they are asking the delta T. What is the difference between T out and T in? Okay, so that is the problem. Let's make the figure first and then we can calculate everything. Fine. So for the first part, that is the reactor and it is already given 1 mole. So let's take 1 mole of methane as the basis. So suppose CH4 is entering, and what is CH4? 1 mole. Undergoes complete combustion in a stoichiometric amount of air. So can you tell me what is the stoichiometric amount of air required for 1 mole of methane? Obviously 1 mole of methane is going to react with 2 mole of oxygen. It means that I'm passing how many moles of oxygen? 2 mole. But here there is an important point. Students are going to make mistake. The question says air, and we know that air means nitrogen is also present. So what is the amount of nitrogen? I hope you can calculate that the nitrogen is given by 2 into 79 by 21. Right? The moles of nitrogen should come out to be 7.524. That is, this all information is given in the problem. Now, what should be the product? It is given that the methane reacts completely. So is there any methane in the product? No. It is also given that only stoichiometric amount of oxygen is given to the system. So whatever oxygen is entering the process, there is no excess oxygen, so it must react. So what should be there? For 1 mole of methane, 1 mole of carbon dioxide must be produced. 2 mole of water must be produced. And if you forget nitrogen, then there is going to be a problem. So 7.524 mole nitrogen should be produced. Now what is asked? That the mole fraction of water vapor. So it means they are asking 2 divided by 1 plus 2 plus 7.524. I hope you can solve this. Let's check your answers. Your answers must be equal to 0.19. Right? That was the first part. Let's solve the energy balance problem. Let me write the delta H value here. Delta H is equal to minus 730 kilojoule. Okay, that is the reaction. Now before writing energy balance, let us check the units of Cp again. It is based on moles, so I can talk about moles. Now each component is having Cp is equal to 40. This component is also having Cp is equal to 40. So how to write balance? Let's see. Delta H is equal to Q external. Fine. And what is the value of Q external here? Q external is not directly given, but there is a hidden word. What is that hidden word? Maximum temperature rise. During a chemical reaction, if it is exothermic in nature, it is going to release heat, right? Now that heat which is released during the reaction can leave the reactor. If it is leaving the reactor, then it's fine. But if it is not leaving the reactor, it is going to increase the temperature of the reaction mixture. Now suppose if during the reaction 500 kilojoule of energy is being released, and if the entire heat leaves from the system, then the reaction remains isothermal. The temperature is not going to change. But if some heat leaves and some heat stays inside the reactor, the temperature will increase. And if the entire heat stays inside the reactor and it is not leaving the reactor, then the temperature of the product is going to be maximum. So in which case maximum temperature will be there? If Q external means that is equal to 0, means the heat which is released during the reaction is not leaving the reactor. So we have to take Q external 0 to get maximum temperature rise. Now, what is the balance? Enthalpy out, enthalpy in. Suppose this temperature is T out, this temperature is T in. You have to find T out minus T in. So you have to take each component separately, multiplied by its Cp, multiplied by its temperature. But because all the components are having same Cp, so I can simply write 1 plus 2 plus 7.524, that is Fi into Cpi, which is 40. Please check the units. This is also mole, right? And Cp is also mole, so there is no problem. That is the enthalpy out. Okay, so multiplied by the temperature, so that is T out minus reference temperature, which is 298 Kelvin. Fine. Minus enthalpy in. What is enthalpy in? 1 mole multiplied by Cp, which is 40 into T in minus 298 Kelvin. Fine. That is the enthalpy in part. Enthalpy out minus enthalpy in plus enthalpy of reaction, which is 730. So I told you that you have to use this along with sign because it is kilojoule. Rest of the values are in joule, right? Even Cp value is in joule. So I have to convert this into joules and multiplied by Fa naught into Xa. What is Fa naught? 1. What is conversion? 1. So it should be multiplied by 1 is equal to Q external, which is 0. From this, you have to calculate T out minus T in. I hope you can easily calculate that the value T out minus T in is equal to, so do the calculations. Please check your calculations first. I hope you are getting the answers, and the answer will be equal to 1730. It is approximately. You may get deviations of 15 or 20 or 30, just depending upon the accuracy which you are using in this problem, right? So that was one problem which explains the concept of both mass balance with chemical reaction as well as energy balance. Let us take the second problem. This problem I have taken from GATE 2016. Let's read the problem. A jacketed stirred tank with the provision for heat removal is used to mix sulfuric acid and water. So it is a mixing process, not a reaction, in a steady state flow process. It's a continuous process. H2SO4 liquid means it's not a solution, it's pure sulfuric acid in the liquid form, enters at a rate of 4 kg per hour, the mass flow rate of H2SO4 at this temperature, and H2O liquid enters at a rate of 6 kg per hour at a different temperature. Okay, the data is given: specific heat of water along with the units, specific heat of aqueous solution of 40% H2SO4, specific heat is independent of temperature, based on different states of H2O liquid and H2SO4 liquid at 25 degrees Celsius. The question has mentioned that what should be the reference state. You should not think about any other reference state. Whatever is mentioned in the question, we have to use that reference state. If not mentioned, then we have to use that temperature as the reference temperature at which the enthalpies are provided. The heat of mixing for aqueous solution of 40% mass H2SO4 is given minus 650 kilojoule per kg H2SO4. If the mixed stream leaves at 40 degrees Celsius, what is the rate of heat removal? So what is the meaning of heat removal? Means the question is asking Q external, right? So that is the problem. Units are provided kilojoule per hour. Fine. Let's make the diagram first. Suppose this is the system, the tank. The liquid H2SO4 is entering at what temperature? 25 degrees Celsius. And what is its mass? 4 kg per hour. The water is entering at 6 kg per hour at 10 degrees Celsius. So first of all, we have to apply mass balance here. Sulfuric acid is 4 kg per hour, water is 6 kg per hour. What should be the mass flow rate of the exit stream? Simple mass balance, 6 plus 4, it should be 10 kg per hour. But this 10 kg per hour, is it completely sulfuric acid or is it completely water? No, it's an aqueous solution. And what is in that solution? In this 10 kg, 4 kg is the sulfuric acid. So what should be the mass percent here? It is 40 mass percent. And what is the temperature of the exit stream? It is given the mixed stream leaves the tank at 40 degrees Celsius also. So that is the scenario, and that is the mass balance for this process. Now let's talk about the energy balance. Enthalpy of mixing is provided. Let us use the same equation. So what is enthalpy out and enthalpy in? So I have used this data, so let us make some space for solving the problem. First of all, enthalpy out, right? So what is the mass flow rate of the outlet stream? It is 10. What is the Cp of the aqueous solution? It is provided in the question, right? So the Cp of aqueous solution is provided, and that is equal to 2.8 kilojoule per kg solution per Kelvin. So mass into Cp into temperature minus the reference temperature, right? That is the enthalpy out. Minus the enthalpy in. What is enthalpy in? The enthalpy with this stream as well as with this stream. So for this stream, the enthalpy must be 0. Why? Because the temperature is 25 degrees Celsius and the reference is also 25 degrees Celsius. And that is why the Cp for sulfuric acid, pure sulfuric acid liquid state is not given in the problem, because it is going to be 0, because 25 is the reference, plus 6 into Cp of water, that was given as, I guess, 4.2 multiplied by 10 minus 25. Do not write 25 minus 10. Enthalpy can be negative depending upon your state, reference state and reference temperatures, right? Enthalpy out minus enthalpy in plus delta H of mixing multiplied by some terms which makes it energy by time. So what was delta H of mixing? Minus 650, and see the unit, kilojoule per kg H2SO4. So how many kgs of H2SO4 we have? 4 kg H2SO4 per hour. So 650 into 4, check the units. Kilojoules per kg H2SO4, and this is kg H2SO4 per hour. So what is the unit? Kilojoule per hour. You can also check the units of other terms. It is also kilojoule per hour. So the units are fine. The equation is correct. Fine. Okay. Now what it should be equated to? Should be equated to Q external, which has to be found in this problem. Now all the data are given. You can easily solve this problem. Always be careful about the units, whether the unit is in kilojoules or the unit is in joule. It is possible sometimes that the enthalpy is given in terms of kilojoule while the Cp specific heat is given in terms of joule. So you have to be careful there. Sometimes the enthalpies are written here in terms of kilomole, and in the case of Cp the units is kilojoule per mole. So you have to be very, very careful while reading these kind of problems. Okay. If you solve this, the value of Q external is approximately equal to 1802. The units must be kilojoule per hour. Okay. So these two problems explain how to use the equation delta H is equal to Q external for energy balance in the case of chemical reaction, as well as for energy balance when there was no chemical reaction and something extra enthalpy, the enthalpy of mixing was given, right? So this was the complete course for the subject of process calculation. You can try to solve all the problems based on the concepts that I have taught in this course. Most of the problems you'll be able to solve very easily in such a short duration of this program, right? If you have any doubt in process calculation, you can comment here, or you can contact me at the number provided in the description or in the mail ID provided in the description.